Hello everyone, welcome to my YouTube channel. I'm Matt and today we are going to build 2048 the game. We are going to use React, CSS transitions, custom hooks. The video will be different than my other ones since we are not going to do the live coding, we will do only the code review. I hope you like this form. Please let me know in the comment section, please hit the like button, subscribe, and let's get started. What are the rules of the game? So the player should combine tiles until they reach the tile with the number 2048. There are some constraints. The tile can only contain integer values starting from the number 2 and being the power of 2. What does it mean being the power of 2? It means 2, 4, 8, 16, 32, 64, 128 and so on. Board is restricted to the size 4 tiles by 4 tiles, so it means there are only 16 possible tiles to be on the board in the very same time. Ideally, the player should reach the finite tile within the smallest number of steps, and if the board is full and there is no possible move to make, the game shall be over. Unfortunately, I took some shortcuts to focus on the game mechanics and animation. So I didn't implement scoring, I simplified the tile generation, and you cannot finish the game, like you cannot complete it. So the winning situation and the lose situation is not handled by my code. If you think this is unacceptable, you can fork my repository and implement it on your own. If you want me, I can review your code, just add my username into your pull request and I will look into it. So now let's get started. Now I'm going to introduce you to the project structure. Our application will contain 4 very important elements. The first one is the board component responsible for rendering the tile and grid. The second one is the grid component which renders the grid 4 by 4 tiles. The third one is the tile component responsible for rendering the tile and also all animations related to itself. The game component is the last one and it combines all those elements together. It also includes the useGame hook which will be responsible for enforcing the game rules and all of its constraints. Since we want to focus more on animation in this tutorial, I will start the story from the tile component. In the end, this component is responsible for all animations in the game. So there are 2 fairly simple animations in our game, such as tile highlighting, and the second one is sliding the tile across the board and then merging it, which is actually the tile highlighting, right? So we can handle those animations with simple CSS transition by declaring the following styles. As I mentioned before, we are going to use CSS transition to achieve animations in our application. So CSS transitions allows us to change the property value smoothly over a given period of time. So what does it mean? Let's look into the code. We have 2 different properties related to transitions. The first one is transition property, and we define following values: left, top, and transform, and transition duration, which we have 3 other values, right? So what is the transition property? So left and top tells us that we are going to transition the position of the tile. So we wanted to animate the slides and we are going to do this by defining this property. What about the transform? Transform actually allows us to scale up and down the tile. So we'll indicate this highlight by using this property. As you can see, the animation of slides will last 250 milliseconds and the scale up and scale down will be 100 milliseconds. Now we are ready to look into the tile component itself. So as you can see, the component accepts only 3 properties, such as a value, which is an actual number within the tile, such as 2, 4, 8, 16, and so on. The second one is a position of the tile on the board. Since our board is 2-dimensional, it has x and y value. We are going to pass the position as an array of 2 elements. The first element will be responsible for the x value and the second one for the y value. Instead of using pixels, we are going to pass the indexes of those properties. What does it mean? Let's look at our board. As you can see, the row represents the x value, and it can take the following indexes: 0, 1, 2, and 3. The column is very similar, but it represents the y value. It can take the same indexes as the row since the board has the shape of square. The last property is z-index, which allows us to define the order of tiles if they are stacked on each other. We are going to use it later on to handle the tile merges. Now you know all properties required to use this component, so we can deep dive into how it's built. Let's get started from the line 18. I am calling a hook that returns properties of the board, such as the length of the container, which are the width and height, it is a square, and the amount of tiles per row and column. I'm going to need those properties to calculate the position of the tile. You can check out the complete code of the hook on my GitHub. It is a very standard implementation of React Context API and hooks, so I will skip that. If you want to learn more about it, you can check out my video on feature toggles. Find the link on the top right corner of this video. In the line 20, I defined the scale state. I'm gonna use it to animate the highlighting of the tile. So we will scale it up and down whenever it is needed to indicate the change of the tile. From the line 23 to 30, we are going to determine if we want to animate the highlighting of the tile. The highlighting shall be triggered when the new tile is created or whenever the existing tile changed its value. Not the position, just the value, just the number within the tile. The use effect hook in the line 33 will be handling the animation for us. It will rescale the size of the tile to 110%, and after 100 milliseconds, it will change it back to 100%. So the tile will have this some sort of bump effect. You might have noticed that I'm using a custom hook called usePrefProps. It helps me to track the previous values of the component properties, the props, so I can indicate if the value of the tile has changed, and then I can react to this. You can find the code of this hook on my GitHub as well. Now, let's look how the position of tile is converted into pixels. In line 43, I created a function called positionToPixels. The responsibility of this function is converting the index on the board into the actual position in pixels. The function accepts only one argument, which is the index of tile on the board. As I said before, the board has a shape of square, so that we need only one function to convert both coordinates, x and y. So how are we going to use this function? We'll simply pass the new position into the style property of the component, just like that. Now you know how the tile component works, so we are ready to go through the board component. The board component will be displaying our tiles and populating the properties of the board to the context API. This component accepts only two properties, and only the first one is mandatory. The first one is the tiles, which contains the list of tiles available in the game at the moment. I will explain what includes the tile meta type later. In the current moment, we only need to know that it includes tile value and its position on the board. The second one is the tile count per row. It tells the board how many tiles are in the row and column. By default, it equals 4, but if you wish, you can change it. So now, we know all properties of this component, so we can review its code. I'm gonna jump around the component's code since it does two different things and the business logic is a bit mixed up, but those two things sort of overlap, so I didn't decide to split this component into two. Let's look into the tile rendering first. In line 20 to 22, we will create an array of tile components which will be rendered in the tile container. What is the tile container? The tile container is a simple div that has only one custom CSS property. The property responsible for positioning called position, and we need to set its value to relative. Why? we want to position every tile in a relative way to the board, so we reach one directional way of control from the parent to the children, not other way around. Now let's look into the second role of this component, which is populating all properties to the context API. In line 17 and 15, I'm calculating the width of the tile container and its board wrapper. I decided to calculate those properties on my own instead of using references to the DOM elements. It was just easier to do it since I know all tile sizes and their margins. Look, the container width equals the width of the tile with all margins multiplied by the amount of tiles. And now the second one, the board width, equals the container width plus margins. It is simple. By following this approach, we made the code easier to read comparing to references. But please don't take it as an argument against references. The references are super important, but in this case are not needed. Okay, let's get deeper. In line 28 and 27, we are injecting the container width variable and tile count per row property into the board provider. What is the board provider? The board provider is a provider coming from the context API. I don't want to dig deeper into context API since I explained it in my previous video on feature toggles. You can find the link to this video in the top right corner now. The most important thing you need to know about context API is that enables us to use declared properties in all children of this component without passing them as props. We are using it extensively in the tile component. Do you remember the position to pixels function? It uses board properties to set the right coordinates on the board. Now you know how the board works, so we are ready to go through the game component. The game component is responsible for connecting all pieces together. It will render the board and link keyboard events with the game engine. The component doesn't accept any properties, so that we will skip this part. In the very first line of this component, you can see a strange hook called useGame. This hook returns the list of tiles and exposes 4 functions responsible for navigation, such as move left, right, up, and down. The list of tiles must be passed down to the board component so it can display them. But the most important role of this component is linking the right keystrokes with actions. In line 10, we have the handle key down function, which maps navigation with keyboard arrows. But you might say, "Hey Matt, but this game will not work on my iPhone." And you are right. If you want it to work on your iPhone, you need to fork this repository and implement it on your own. It is a nice exercise that will let you dig deeper into the code and understand it better. But before you do so, smash the like button, click subscribe and notification bell. In line 31, I throttled our function to be sure the player will not be able to flood the game with tons of keystrokes. Our game has beautiful animation and we want our players to admire them. And also, our logic of the game is built based on reduces, so we really need to have all events completed, because otherwise the game will be broken. Do you see this use effect in line 37? I have bound our function into the window event listener there, so it can listen to keyboard events. Otherwise it will not be possible to do this. As you can see, this function returns the callback that removes this event. It is required to prevent memory leaks. This callback will be called when the component will be destroyed. When it can happen? When you click the reset button, for example. Now we are reaching the core of our game, the useGame hook. As I said, the useGame hook will be dealing with the game logic. I split it into 2 parts, the reducer and the hook. We're gonna start from the reducer since it will be storing and manipulating the game data. The reducer requires 2 arguments. The first one is the state and the second one is actions. Let's dig deeper into the state first. As you can see, it contains the following fields. The tiles. It is a hash table responsible for storing the tiles. The hash table makes it easy to find entries by keys. It is the best match for us since we want to find our tiles by IDs. Now, it is a good time to explain what the tile meta type actually contains. It has an ID, which is a unique identifier. We'll need IDs to merge tiles with each other, but they have also another important role. They help React DOM to detect changes in the right tiles rather than re-render all of them from scratch. The second one is the position. It is exactly the same position we discussed along with the tile component, simply the row and the column index on the board. So for our size of the board, it might have values from 0 to 3. The third one is the tile value. It can have values from 2 up to 2048. The last one is the merge with property. If this property is present, the tile will be merged into another tile. The property can be undefined, or it must contain the ID of the tile which is going to absorb the current tile. So we needed to extract this property since we want to run two animations one after another. So the last one needs to be delayed. How it works? First, we want to let the tile slide onto another tile, and once the animation is finished, we want to destroy the tile and update the destination tile. Now you know what the tile meta contains, so we can continue with the state definition. The second property of the state is byIds array. This array contains all IDs of the tiles in the expected order, it means ascending. It will help React DOM to update only the tiles that have been changed. The third property is the hasChange flag. It keeps track on the tile changes. As you know, on every move, we want to add a new tile to the board. So this property tells us if any tile changed their value or position. If they don't, the new tile will not be added. The last property is the inMotion flag. It determines if tiles are still moving. If they are moving, the new tile will not be generated until the animation is completed. Now we are done with the state, so it is a due time to discuss the actions. We'll support 5 different actions in this reducer. The first one is create tile. It creates a new tile in the hash table and sets the hasChange flag to false to indicate that the new tile was already generated, so there is no need to create a new one. The second one is update tile. It updates an existing tile and sets the hasChange flag to true to notify that we want to still create a new tile after animations are completed. The third one is merge tile. It merges the source tile into the destination tile. The source tile will be removed from the hash table and byIds array, and also it changes the hasChange property to true. The next one is start move, and it tells reducer it should expect multiple updates, and it must wait until all of them are completed to keep the consistency of the animations. The last one is end move. It tells the animations are completed so we can safely add a new tile into a hash table. Now you know how the reducer handles actions, so we can dig deep into the hook. The hook will be mostly dealing with navigation, so I'm gonna explain now how I implemented the move function first. The move function will perform the board transformations such as tile moves and merges. It accepts 2 arguments. The first one is the retrieve tile IDs per row or column callback, which is supposed to return all tile IDs within the row or column. It depends if we transform the board horizontally or vertically. The second one is the calculate first free index callback. It's supposed to return the first free index in the row or column. We need it to calculate the new indexes of tiles after board transformation. It might sound a bit vague, but hopefully it will get clear once I explain the logic of this function. In the very first line, we can see I dispatched the start move action to lock the board, so no new tile can be created until it is released. As you can see, I'm gonna dispatch the end move action at the end of this function. So I will delay this dispatch by the duration of all animations, so animations have time to complete. In line 111, I declared the max index in row or column. I will need it to calculate the first three position of the tile. In our case, max index equals 3, since the board is 4 by 4 tiles, and all indexes start from 0. In line 114, I'm gonna iterate through every row or column to merge and update tiles. In line 123, we'll use the first argument of the move function to retrieve all tiles in the row or column. Once we have our tile IDs in line 131, we're gonna iterate and transform them. In the line 132, we will create a reference to the current tile, which we are going to use to create a new tile object in line 156. As you can see, in line 156, we are going to use the second callback we injected into the function. I skip explaining the parameter of this for now. We'll return to it very soon though. In line 172, we check if the tile was moved, and if so, we are going to update it. But you may say, hey Matt, but you skipped some parts of the code here. You are right. Let's return to line 126. In line 126, I declared the previous tile variable, which I'm gonna use to detect merges. In line 128, I defined the variable to store how many merges happen in this row or column, so I can correct the position of the next tiles to fill the gaps. In line 135 of this for each function, we'll check if the previous tile has the same value as the current one, and if it does, we're gonna schedule to merge those tiles together. As you can see, the merge tile action is throttled, so it waits until the moves are finished and then it performs the merge. In line 148, we clear the value of the previous tile variable, so we allow for only one merge per tile per move. In line 150, we'll increase the merge tile counter by 1 and then we'll update the tile. Finally, we are reaching the very last function of this game. We will focus only on one move function, since all the other ones are almost the same. The only differences are if they are dealing with the columns instead of rows, or from which directions they calculate their indexes. Let's get started. As you can see, I declared the move left factory function, which will create a move left function for us. In the very first line, I create a helper function that will return tiles in the row. It accepts only one argument that says from which row index we want to get tiles. We are using rows since this is a horizontal transformation. If we will create move up or down factory function, we will operate on columns rather than rows. In line 197, I declared the calculate first free index helper that will calculate a new position of the tile. We just need to pass the tile index in row, the amount of merges in this row, and the max index isn't really required in this case because the move left function doesn't calculate stuff from left to right. Obviously, this helper will be different for other directions, but I want to focus on one only to simplify the review process. And in the very last line of this function, we are binding those helpers into move function. This technique is called inversion of control. What it does? It allows a developer to pass a custom code into the function to manipulate its execution. It is a very important design pattern, so you should learn it. So if you want, go through the code on your own as well. You can find it on my GitHub. Now, let's look at the bottom of our hook. As you can see, we initialize all moves through their factory functions and return them as the output of the hook. And that's it for today. I hope you enjoyed the video. Let me know in the comment section. Please hit the like button, subscribe, and stay tuned for the next episodes.